All right, let's get this thing started. Let me know in chat if you can hear me. Just making sure my sound's good before I go talking for an hour. Can you hear me in chat? Awesome, thank you. Well, did I at least get the date right? March 9th, 2021. Thank you for coming to Free GMAT Prep Hour this evening or this morning, depending on where you are. Or the afternoon, maybe, the afternoon. Remember that you have some additional free resources you can take part of through Manhattan Prep. Just go ahead to our website here, manhattanprep.com/GMAT/resources. There are a handful of free options, free resources there. If you're interested in the GRE or LSAT, just substitute GRE or LSAT for GMAT in the link here. Would love to see you at a trial class. Come to session 1 of our 9-session course and learn a little bit about what the GMAT is all about, how it scores you, how to get your kind of mind prepped for this strange exam, learn a little bit about data sufficiency techniques and sentence correction methods. And you can see kind of all the resources that are provided with the course. You could also come check out the first few lessons of GMAT Interact, which is our kind of more of our self-guided study course, and see if this is kind of an option that sits with your learning style and learning preferences. So thanks again for coming, and please check out these other free resources. Let's go ahead and get to the content of the day. The content of the day is going to be a lesson on standard deviation as it's presented on the GMAT. We are going to talk about what standard deviation is, because it's kind of a tricky concept a little bit. We're going to talk about if we need to calculate it, conditions where we might have to, conditions where we won't. And then I want to give you kind of some problems to tackle. There will be some smaller problems along the way. And then towards the end, I have at least a 3-question problem set to give you. I do want to mention, though, that I am not just talking about standard deviation and going through like lines and lines of text. This emphasis today is going to be on trying to visualize what standard deviation represents. And so we're going to be like looking at number lines to kind of help understand like the spatial aspect of data sets and how that kind of can influence how we think about data, how we think about standard deviation. So I'm excited to talk about this with you, and excited to show you all my PowerPoint visuals. This is just an excuse for me to like move things around on the PowerPoint slides. So thanks for coming. I see a couple people are showing up a little after we started, but welcome, welcome. Let's talk a little bit about what standard deviation is. Go ahead and type in the chat to me what your conception of standard deviation is. What does standard deviation mean? What does it do for us? And you can type this and send it to me alone. You could send it to the whole group. Just kind of interested in getting some insight into how you think of standard deviation at this point. I like it. Average distance to the average, kind of, yeah. A meta average problem. Distance from the mean, yeah. I think kind of understanding it has to do with spacing and how far things are away from the average of a set. Here's kind of one way to think about it. Standard deviation is going to be like a measurement. Okay, it's always in some like distance or units that tells us in general like where the data points sit in relation to their overall average. And again, this is kind of a tricky concept to just talk about, so I want to go ahead and take a look at some examples. So maybe the most kind of common setting that you've talked about standard deviation has been in relation to what's called a normal distribution or a bell-shaped curve. All right, it's important to note that not all data sets are normal distributions, okay? But normal distributions are kind of like these idealized data sets that kind of look like this, where there's an average value and more values in the set are close to the average than they are like farther away. As you get further away from the average, the values start becoming like a little bit rarer. in the set. And so what standard deviation tries to do is, at least in a normal distribution, is it actually is defined by saying, look, a standard deviation is a window within we expect to find a certain number of the values in the set. Okay, and so how that works for standard deviations is within a standard deviation above the average or below the average, you expect to find a total of like 68, right around 68% of all the values. Okay, so it's almost like, think about these like a standard deviation here, this length is like an arm, right? And how far does it reach through the data sets? How many things are available to it in its grasp this way or in its grasp this way? Okay. If we extend, a normal distribution and a bell-shaped curve, I would say are the same. Normal distributions are always symmetrical, but not all symmetrical distributions are normal. A normal distribution is like a very special type of symmetrical distribution. Yeah, and we're going to look at the data sets today that just aren't even symmetrical in the first place. So if we go out another standard deviation, so let me get like a different color in here. As we go out this next unit, all right, we expect to cover more of the values in the set. So by the time you extend 2 standard deviations out from the mean in a normal distribution, you've now accounted for like something around 95% of all the values in a set. And this continues. Like if you kept going, I didn't draw it here, but like a third standard deviation would extend, pretty much to where the curve vanishes into the x-axis. You'll have accounted for nearly 100% of the values, 99.7% of the values. Okay, but it's important to remember that this might be like the original context you learned about these things, but data sets on the GMAT are not always normally distributed like this. So what is standard deviation? We mentioned that it's a measurement that indicates like how far from the average these data points might fall. Another way of thinking about it is a standard deviation is this measurement that shows kind of how data points are dispersed around the average. And the way to kind of think about this is the closer the data points are towards the average, we'll say that there's a smaller standard deviation. And then as the wider the data points are spaced around the average, the standard deviation will just be higher. And kind of this is an important 2 bullet points to understand here, right? More clustered values towards the average means lower standard deviation. More widely dispersed values around the average means a larger standard deviation. So let's take a look at some sets that kind of illustrate this. So let me move these points up top and let me present to you set A and set B. Go ahead and take a moment and try to determine the average of each of these sets. You can let me know in chat when you have it. Yeah, Mamadou, nice. Yeah, I tried to pick some easy numbers. Wouldn't have to do too much math, but we could see that in set A, the -2 should cancel with the +2 and give you like a subsum of 0. And then the negative ones do the same with the positive ones. And so the average on the left, it will be 0 because the sum is 0. It's actually the same thing for set B. The negatives add up to -14. And the positives add up to +14. So it's all a wash here. Okay, so if the sums are 0, then it doesn't matter how many terms are in each set. There are 9 terms in each set. It doesn't matter. The average is 0. So we can actually calculate the standard deviation for this. But what I want to show here is that the standard deviation for set A is just smaller than that of set B. And we can confirm this by just kind of visualizing these points on a number line. So we're going to do this with some color. Here's a number line from -7 to +7, and I'm just going to plot the values of set A. What we can see here is they're relatively close to 0. This is a symmetrical set. It's not necessarily bell-shaped or a normal distribution, because we just don't have enough data points to really like make that claim here. It looks like a triangle, but we can see they're relatively clustered together on the number line. Whereas if you plotted the values in set B, think about what this would look like before I put them on the number line. They're a lot more widely dispersed, right? Their average is still 0 because we kind of like found the sum was 0 earlier, but we can see that they're more widely dispersed. And so it makes sense that the standard deviation for set B is higher than the standard deviation for set A, right? These are more clustered. These are further apart. Okay, so how did I arrive at these standard deviations though? Is it just like I just waved a magic wand and voila, we had it? So how are we going to calculate standard deviation? Well, the good news is on this exam, you probably won't really have to do it. Okay, there might be like occasional really small sets of numbers that we have to determine the standard deviation of, but in general, the GMAT's not interested in seeing if you like know all the rules for calculating standard deviation. They want to see if you like understand the concept at a deeper level. Okay, but because we are going to practice visualizing today, I am going to walk through the steps for how to calculate standard deviation so you can kind of see where this stuff is coming from. So there's a list of steps here. I'm going to go ahead and lay them out. Then we're going to walk through an example and actually calculate like a standard deviation of a set, and we're going to visualize it as we go. So the first thing to do is to figure out the average of the overall set. And then we are going to figure out like how far each term is from the collective average. And I was getting some suggestions about this, that this had to do with standard deviation for sure. Good. Once you've got all those differences or distances from each term to their average, you are going to square them. After we square them, we are going to add up all those squared values, sum them up, divide by how many terms we had. So steps 4 and 5 here basically amount to finding out the average size of the squares. And then after we found the average size of those square differences, we are going to square root. And that will give us the standard deviation. So let's actually like walk through this, and I want to show you what this looks like related to a number line. So here are 7 terms. Step 1 is to go find the average. The average is not 0 this time. I changed it. So go ahead and go find the average. Let me know in chat when you have it. All right. This is reading some comment that came in the chat, and it's a little intense for me right now, so I'll take a look at it later when we've got more time. All right, so we found the average should be 2. Yeah, we add these up, -3, -2, cancel out with 5. The 1 and the 9 are 10, plus 4 is 14. There's 7 terms, average of 2. So the next thing we're going to do is we're going to find the difference between each term and the average. Go ahead and take a moment, try to figure out how far each term is from the average. Maybe just kind of make a list because we're not done with these terms yet. You're welcome. So I like to visualize this on the number line. We're probably doing some subtractions, like what's the difference from -3 to 2 and -2 and 2. I'm going to just show this out on the page here. -3 to 2 is a distance of 5. -2 to 2 is a distance of 4. And we can kind of just see how long these lengths are on the number line. All right, so maybe we have all these differences now. The next thing we're going to do is we are going to square them. take a moment and actually like try squaring them. I mean, at least they're all integers and they're single digit integers. So we should have these squares on pretty quick recall here. This one looks like it's going to be 5 by 25, 4 squared is 16, 2 squared is 4, 1 squared is 1, 2 squared is 4, 3 squared is 9, and the big one's 7, 7 squared is 49. So we're going to square these things and then we're going to picture them out. Okay, so I've made little squares here. And then now that we have all those square sizes, the fourth step is to add up the squares. So we had like 25 and 16 and 4 and 1 and 4 and 9 and 49. We got to add those up. You can take my word for it, or you can check on your own. The sum of those will be 108. So if we put all these into one giant square, it would be about this big. Can you believe that? Like all of these squares, if you added them and smashed them together, like they would turn into a square this big? No, maybe it's hard to believe. I measured it out. And then the next step is to, remember, divide by how many terms there were. So there were 7 terms. So we're going to break this square and try to, like, imagine you're working with like dough here. You're like going to break this up into 7 equal pieces. Well, you could make 7 squares of this size. And what that means is this square was the average size square here. We summed them up, divided by 7. So the 7 squares on the page here have an average size of this square. Okay. So that was like 100, an area of 108 divided by 7. So we're like at 15 3/7 now. And the last step is to square root. And so the visualization of square rooting a square, yeah, I think Manuel's got it, like about 15.42. If you know you're repeating sevens, yeah, 15.428571 forever. And then we're going to take the square root of this square, and that just means go find the length, right? The square root of a square is its side. And so if we take the square root of 15 3/7, we get something that's like a little less than 4. The square root of 16 would be 4. The square root of 15 and change would be just less than 4. Okay, wow, okay. Why did we do all that? Like, what does this really mean? Well, it means like on this number line, this distance, which is, you know, just under 4, about 3.95, is the value that like you'd expect a certain percentage of, there's like a certain expectancy of like how many values in the set kind of fall 3.95 above the average and within 3.95 below the average, and etc. Like 2 standard deviations above, 2 standard deviations below, things like that. So this is how standard deviation is calculated. All right, but I just said, like, you're probably not going to have to calculate standard deviation. You definitely won't have to go through that on the GMAT. Like, that's too many like little tedious steps, and the GMAT's really not interested in you being able to do that. Okay. So more likely is that the GMAT is going to give you the standard deviation, and they're just going to say, like, look, in this set, the standard deviation is 3.95 or something like that, and the average is 2. And then they'll ask you a question related to that given information. So that question might look like this. Which values in the set are within 1 standard deviation of the mean or the average? So go ahead and take a moment and consider this question. Try to figure out which values are within 1 standard deviation of the mean. Mama, do close. Yeah, and I have a question that came into chat, and so I want to go get that real quick. Yeah, let me see. All right. Yeah, so the question came, it's like, so what does this line really indicate? Like, what does 3.95 mean? It's hard to really say specifically what it means. I mean, if I wanted to describe it, I'd be like, it's the square root of the average distance squared from the mean of all the values. Like, and that's like, that means less than nothing to me. But it basically communicates that 3.95 somehow kind of captures this idea that the numbers are a certain spread from the average, where if the standard deviation were like 0.95, 0.95, I would now know, oh, the values are like more closely packed. So it is kind of abstract here. It's a little like, I don't want to say it's like out of touch, but it's not like a super obvious thing, like how to connect this standard deviation to these terms and ask like what it represents, other than saying it kind of describes how widely spaced they are. All right, so on this number line, we've got 2 as our average, and we know a standard deviation is about 3.95. And so what that means is, like, again, think about 2 as like maybe where you are right now. And a standard deviation is like an arm's length. Like, how far can you reach with your arm, like in either direction, right? Is 4 within 1 arm's reach or 1 standard deviation from the mean? And it looks like it is. Yes, it's kind of, we pass 4 on the way to 5.95, which is like the furthest we can reach to the positive end on the number line in 1 standard deviation. But I also want to check like how far I can reach to the left. I realize like now I'm like looking at you, and so when I'm doing this, I am pointing negative, and this way is the positive. But I want to make sure I'm looking at both directions in the number line. Okay, and so what we're going to do is we're just going to add the standard deviation and subtract the standard deviation to and from our mean and say, look, 1 standard deviation above gets me to about 5.95. 1 standard deviation below gets me to almost -2, but not quite. And so the values that are kind of contained within those like arm's reach of 2 are 0, 1, 4, and 5. Like 9's too far, right? Like you can't get there with 1 arm's reach. Maybe if I had like 2 of these arms, I could reach it. And same thing with like -2 and -3. They're just like out of reach. There are more than 1 standard deviation away from the average or from the mean. Yeah, there are like differences between standard deviations and like interquartile ranges. So interquartile ranges, quartiles are going to be more based on not like averages, but like medians, and like medians within halves, right? So we're talking about like what's the median is like the 50th percentile. We know that median and mean are not necessarily the same thing. They are in bell-shaped curves. They are in symmetrical distributions, but like this set is not symmetrical. Right. So it's another way to kind of like think about interquartile range. Like remember, interquartile range captures 50% of a data set, whereas generally speaking, in large data sets, a standard deviation in either direction should capture like 2/3 or more than 2/3 of your data set, about 68%. Cool, let's try another question. All right, so again, we're given the average, we're given the standard deviation. How many standard deviations from the mean is the greatest value in the set? This is like another type of question they could ask you with this given information. I'm interested in knowing some of your approximations. Let me know in chat. Yeah, Tyler, that sounds pretty good. Yeah, it depends. I mean, to be fair, this is not a real GMAT question because there aren't answer choices and there aren't data sufficiency statements, but just try to estimate. Yeah, Kashyap, I think that's pretty good. Yeah, Mamadou, I think that's pretty good. Yeah, Caleb, I think we're on the same page here. Yeah, so again, we could like visualize this a little bit. and try to figure out, okay, one, the standard deviation above the mean doesn't get me to my greatest value, right? It gets me to about 5.95. So then if I add another standard deviation length to this, like I'm actually gonna overshoot the greatest value, right? An extra 3.95 above 5.95 is about 9.9. And so the answer should be less than 2, right? I think if you approximated 2, that's pretty good. The answer is going to be less than 2. So one way to think about this is like, how many of these line segments does it take for me to get to 9, right? Well, each line segment is 3.95. So like, how many 3.95s to traverse the distance from 2 to 9, which is a distance of 7 spaces on the number line. So how many 3.95s equals 7? Well, that's kind of like asking 3.95, and this should be like 9 fives, X of them will get me to 7. And so to solve for X, I would just want to do 7 divided by 3.95. And that's close to 7/4, which is 1.75. This should be a little bit more than 1.75, because if you decrease the denominator in a fraction like this, if you make its magnitude smaller, then the magnitude of the entire thing gets larger, right? Like 7/3 is bigger than 7/4. So 7 over 3.95 should be like a little more than 7/4. Yeah, so a question came in about like this set versus a bell curve. Remember, this set is not a bell curve, right? It is not a normal, it doesn't represent a normal distribution. They're just kind of like, I don't know, I wouldn't say they're random values, but they're like kind of random values I picked out. Like when we see these bell curves, let me try to go back to the correct slide here. I don't want to be like hopping around and showing you like bad slides. If we go back to like this bell curve, like imagine like what would be a decent data set here? I'm gonna make this up. Let's say like thousands of 3-year-old male golden retrievers were weighed. All right. And we have like data relating to like how many pounds they weighed. Let's just say like the average weight was 70 pounds. And they've been like, their weights are distributed so that like 70 is like the most common weight. And as you get further and further away from 70, the weights get rarer. And so we'll say like, what if the standard deviation here, I have no idea, this is like completely made up. We'll say the standard deviation is 9 pounds, okay? And so what this would say is like, between 61 pounds and 79 pounds, you'd expect to find like the weights of 68% of these 3-year-old male golden retrievers, okay? And then like, if you extend it a little bit further, like by another standard deviation, you'd say, okay, between 52 and 88 pounds, we'd expect to like find 95% of all the golden retrievers that were weighed. And then we went even further, right? These are big and small dogs. Even they're not puppies anymore. They're 3 years old. But you'd expect to say, oh, between like 43 pounds and 97 pounds, you'd find like 99.7% of all golden retrievers. And that actually means like above 93 or above 97 pounds, you'd expect to find like half of the remaining 0.3%, because the other half would be below 43 pounds. Yes. So that is like what we mean by the distributions and the percentages in a bell-shaped curve. But the problems that I've been showing you are not like, this is not a normal distribution of numbers. So we can't say like the chance of us picking 9 from the set, like 9 represents like only 5% of the set because it's so rare. No, it's 1 out of 7 values. So unless you're dealing like, throw those 68%, 95%, 99.7% things out the window, unless you're dealing with a normal distribution. Yeah. Not all sets are normal. Some sets are very weird. All right, hope that was a little clearer. All right, I want to talk about how standard deviations change, all right, by making some adjustments in the set. Now, this is another way that the GMAT can kind of like test you on things. Like you don't have to calculate the standard deviations of the first 8 prime numbers. They might just like tell you what it is and then ask you, okay, if the standard deviation of set A is X, like what's the standard deviation of set B? And I'll give you set B in terms of X, like related to X. Or here's set C, do the same thing. Let me give you a couple minutes to think about this, and then we'll visualize what's happening as we change these. You can let me know in chat when you have answers for one of the two or both of the questions. Yeah, if you have a question, just let me know in chat. If I don't think you want to assume that sets are normal or not normal, well, maybe you could assume they're not normal unless it's been told to you. They will have to tell you that a set has normal distribution in order for you to infer those like 68% within one standard deviation facts. Nice job, Abby. Yeah, you're welcome. Great. All right, I'm going to go ahead and start kind of talking through this. If you are watching on video, just go ahead and pause if you need a little bit more time. But let's go ahead and talk about set B first. Set B. Set B's standard deviation is the same as set A's. Yes. Why? Why is that the case? Good. Yeah. So saying the delta is fixed throughout set A and set B. Yeah, or meaning the change from term to term is constant. Yes, every term in set B is just 10 more than the corresponding term in set A. Well, are we sure that doesn't change standard deviation? Like I noticed that. Are we sure that doesn't change standard deviation? Well, let's kind of take a look at it on the number line. Here's set A. Okay. And set B can be laid out in like an identical spacing, just shifted 10 spots to the right on the number line. So it's like we have this like, I don't know what I'm gonna do with my fingers here. We have this like certain spacing of set A on the number line. And all we're doing here is we're just like moving them down the number line 10 spots. And so the spacing is all the same. And that means they should be spaced around their average or their mean identically. So we can actually calculate this. Okay, you can add all these up, divide by 8 terms. So the average is 9.625. You can do all those measurements with the squares and sum the squares and divide the squares and square root and get the segment. The standard deviation here would be about 5.98, which again, like abstractly kind of communicates roughly how dispersed the values are around 9.65, which of course like isn't even in the set. All right, so this is rather abstract. Okay, but if we do this with set B, we'll find like, oh, the average just shifts up 10, right? The average changes because every term has gone up by 10, but the spacing remains exactly the same. And so the takeaway here is if you change all the values in a set by a same like constant amount, if you add or subtract a constant amount from each value in a set, the average will change, but the standard deviation will not. Has no effect on standard deviation. Just think of it as just like sliding the points on the number line. Their relationships to themselves don't change, and that's what standard deviation is about. It's how the values kind of relate to themselves, not their specific position on a number line. So let's now look at set C. What is the standard deviation of set C? Standard deviation here is 3x. It is 3 times what it started as. Okay. Yeah, those are like, so a question just came into chat. Do we have any shortcuts for finding standard deviations? Because like doing all the squares and adding them and dividing and square rooting is just like it takes a lot of time. Yeah, the shortcut is like you generally don't have to do it. So when I like provide to you here, like these standard deviations, like you would not have to do this on the exam. I'm just showing them to be thorough and showing like, yeah, this distance, this like length of about 6 kind of captures like the arm length of this set. So set C has a standard deviation of 3 times set A. And again, we could show this on the number line. So what I'm going to do here is just kind of plot these points on a number line, but like I can't make the number line really, really long because my screen is not, I don't want to landscape this to the extreme. So I'm going to just kind of make each mark a unit of 3. And when we plot the points here, we'll actually notice, hey, they align perfectly with set A's. And that's just because there is a constant factor of multiplication that's happening as we go from value in set A to set C. I've just increased each of them or multiplied each of them by 3. And so what this has the effect of is, well, the average is still going to be kind of like in a relatively similar position, right? It kind of perfectly aligns with this average on the page. And the spacing here, like if we kind of ignore the number lines on the bottom, the spacing looks the same as well. So the standard deviation line should also be the same length. But now, because all of the values in here, all of these gaps were a distance of 1, and all of these gaps are a distance of 3, this line should cover 3 times the amount that this line covers, right? So the average will be triple, and the standard deviation will be triple as well. Yeah, the reason this isn't 17.94, because that would be 3 times 5.98, because like I had to round this up to get to 5.98, and the rounding didn't work when I multiplied by 3. Yeah, yeah, good question that came in. I'm drawing this on the right to show like one standard, like the length of one standard deviation. To be fair, this is one standard deviation from the mean and to one standard deviation above the mean. It's kind of like arbitrary that I drew it over here. I could have drawn it to the left the same distance. Okay, I think it might be misleading to kind of like put it to center it on the average, because that would be half a standard deviation above the mean and half below the mean, and that can get a little tricky. But it is arbitrary that I've shown it just to the right of the average. Yeah. Yeah. Good. I think another way to think about this, like if this multiplication thing is like a little weird, just like imagine these values represent like in yards, and these values represent like in feet. Like say like we had a paper airplane throwing competition, and we like threw a bunch of paper airplanes. Like here are the distances they went. They were just very conveniently all integers. 2 yards, not very good at throwing paper airplanes. This one's killing it. 19-yard paper airplane throw, really, really good. If I had chosen to capture the data in feet instead, like you'll see that there's just a conversion from there's 3 feet in 1 yard. Right? And so a standard deviation of 5.98, just about 6 yards, should be just about 18 feet. So that's kind of another way to think about what's happening here. All right, takeaway here. We said addition and subtraction of a constant amount does not change standard deviation. If you multiply or divide all the values in a set to get to a new set, the standard deviation will also change by that factor. So if I divided everything by 5 here, and like 0.4, divide everything by 5. Let me think about that. Yeah, 0.4, 0.6, 1, 1.4, etc. Then the standard deviation would be just under 1.2, a fifth of this. Yeah. Good. All right. I think we're ready to look at the set. All right, we're ready to look at the set of problems. You guys have waited for 40 minutes. I have a set of 3 standard deviation related questions. Some of them are like based off of questions that kind of came in when I asked the group a couple days ago for some questions they were working on related to standard deviation we're having trouble with. So I'm going to present these 3 questions to you. These are all made up by me, although like they may have been influenced by ones you've seen before. Let's go take a look at them. You'll have 6 minutes to try them all, right? 3 minutes per question on average. I'll give you 6 minutes here and then let me know in chat when you have answers. If you're working at home and the 6-minute timer runs up, just feel free to pause if you want to keep working. I'm going to catch up on some of these chat questions. That's been just over 2 minutes. You have 2 minutes left, 2 minutes. Got about a minute left. Okay, that has been about 6 minutes here. Yeah, these questions are not easy. And I do apologize for, I feel like I give a lot of tough questions in the sets when I run these hours, but I want to make sure that they provide value beyond just like an introductory lesson. But you can come back to this in a couple of weeks after you've studied up on it and then still kind of and still struggle here a little bit. Let me just double check this question that came into chat. Yeah, this is a good question, Caleb. Thanks for bringing it up. And to be fair, it's a question that came in. Someone else brought it up too, and I answered in chat. How many questions are you going to see related to standard deviation on the GMAT? I wish I knew. I was saying we could. I wish I had the data for that, and we could find the average number of standard deviations that are on the exam and then figure out what the standard deviation of that value is. I would guess 1. I mean, there's so many topics on this exam, but I would say 1, give or take 1. If you got 3 standard deviation questions on a GMAT, I would be absolutely astounded. That would be 99.7th percentile. How much time should you put into mastering this topic? I mean, it kind of depends on what your goals are. I think some people are perfectly fine just saying I'm totally comfortable getting these questions wrong. I will say though that it would probably pay to understand the basics of standard deviation a bit. So knowing that multiplication just of an entire set alters the changes the standard deviation by the same factor, addition and subtraction do nothing, things like that. I would try to understand what standard deviation kind of represents, and I think visualizing it should help a little bit. But to be fair, it's one of these topics that if you're really struggling with it, you don't have to master it to get a goal score on the GMAT probably. But any topic you are kind of throwing the towel in, we might just need another topic to kind of make up for it. So kind of start thinking about that. We can't start throwing away all the standard deviation questions and all the probability questions and all the rate questions, and all the overlapping set questions and all the quadratic questions, because then there's not going to be that much left. So kind of pick and choose. And I think the best way to do it is kind of make sure you learn the basics of all the topics so that you're not missing a really easy standard deviation question on the exam, because that could really hurt. All right, let's go take a look at question 1. Question 1. All right, so we're given some information here. We're given a lot of information, but a lot of important information is given to us in the STEM here. We know the average score is 75, and they just tell us the standard deviation is 8. We don't actually have to calculate standard deviation here. Additionally, we don't know, the standard deviation of this selection might not be 8. The average might not be 73.5, right? These are the averages and standard deviations of the overall kind of data set, and we just have 16 of the exam scores here. Maybe this is the 16 students who sat in the front row of lecture. Remember when you went to lecture? Yeah, the front row of my Zoom class. All right, so what we're trying to do is figure out how many of these scores are within 1.25 standard deviations of the average. Well, let's just go figure out what 1.25 standard deviations is. 1.25, that's 5/4. So I'm going to say that 5/4 of a standard deviation here, 5/4 of 8 is 10. So how many of the scores are within 10 of the average? That's probably how I want to think about this. How many scores are within 10 of 73.5? And maybe I just kind of rephrase that again. How many scores are in this range from 63.5 to 83.5? Right? So this is just like, and we talk about data sufficiency as being like the problem area where we want to do lots of rephrasing, but we're rephrasing a lot in problem solving too, right? We're translating, we're converting, and we're able to kind of change this original question into one that's a little bit more concrete. And then this is the counting game. Like, I don't think there's a real shortcut here. We just need to go through and find the ones between 63.5 and 83.5. So we'll just go row by row. That one works, that one works, this one does not. And 84 like just misses the cut. And no rounding up here. We're not going down to 63 and up to 84, no rounding. 81 works, 72 works, 75 works, 89 does not. 83 just makes the cut, but 63 does not. It's kind of like 84 here, it just misses out. 77, 74, 56 is too low. 73 and 80. So it looks like I have 10 that are in the range, 10 hearts here, and 6 that are not. I believe the answer here is 10, answer C. So let's go ahead and visualize this. Like what we mean like by standard deviation of 8, an average of 73.5. Like we have all these points here, these plots on our number line. Here's our average, and we want to extend our arms. Like normally the arm extends 8, but we are stretching. When we've been doing our yoga, that's a lie. I'm the most inflexible person ever, but we are going to be able to stretch not just to 8 on either side, but to 10 on either side. And so what that looks like here is we're able to go all the way down to 63.5 and up to 83.5. How many of these dots are in that 1.25 standard deviation wingspan on either side? 10 of them. Yeah, good question. If 83.5, what if someone got 83.5? Would it count as within? I don't know. That's kind of like when they tell you like, how many integers are between 21 and 28? Like, is it 6 or 8? Like, I don't know. Like, do I count 21 and 28 or do I not? I think it would be unfair for them to expect you to know that without further clarification. And so that problem probably would be deemed unfair. Probably what would happen is like lots of people would include 83.5 and lots of people wouldn't. And that would show that this question is unfair. And so they would have to revise it. That's why I made the average and a non-integer and the standard deviation or the multiple of it an integer, so we didn't have to deal with that. That's my sleight of hand way of not dealing with the harder problem. Cool, let's go with question number 2. Now I know that there's some there's different ranges of data sufficiency comfort out here, so I'm going to apologize in advance because I'm not going to go through like all the ins and outs of data sufficiency. So I will kind of go through my normal process of tackling statement 1 and tackling statement 2 and trying to prove them insufficient. So remember here, like we're asked a question about standard deviation and we're not given like any values. So we are not trying to like find the standard deviation, right? We can't, there's no values here. We just need to kind of think about the big conception of it. So we don't need to tackle it here. We want to instead kind of rephrase what this really means. What would it mean for the standard deviation of the values in list A to be greater than the standard deviation of the values in list B? Well, it would mean that list A's values are more widely spaced around the average than the values in list B are, right? So this is like asking, are the values in list A less cluttered or more dispersed than the values in list B? Or you could kind of flip this to the exact opposite, right? Are the values in list B more clustered towards their mean than the values in list A are towards list A's mean, right? But we don't have to calculate here, right? We're just trying to think in general. Standard deviation is about how values are dispersed around the average. It's asking, is the standard deviation greater in A? That means, are the values in B more clustered? I think rephrasing that is super key. Let's go tackle our statements. So I want to put these on a number line because I want to try visualizing this. The range of values in list A is greater than the range of values in list B. Okay, so I'm going to go ahead and just use a blue dot to capture list A values, a red one to capture list B values. And let me just make sure I satisfy statement one. Imagine like the range of values in B is very narrow, right? They're kind of close together, and the range in list A is very wide. In this case, are the values in list B more clustered towards their mean than the values in list A? Yeah, they're very clustered. And on this number line, the blue ones are not clustered. And so the answer here is yes. So now I want to see, is there a way I can manipulate statement one in such a way that I get the red values like less clustered, right? So let's try this again. Like, let me try to space out the red values far. I still have to follow the rules of statement one though, right? So I still have to like make sure the range of statement one is wider than the range of values in A is wider than the range of the values in list B. But now I'm trying to figure out, like, is there a way I can like get A's values more clustered towards the mean than B's values? And it's just like, yeah, let me just add a bunch of values in A, like towards the middle. I added 9 here. Imagine there were like 9,000, right? There were like 9,000 values right here and just like 2 outliers. You know, standard deviation is going to be relatively small compared to B's, which is pretty wide. Right? Imagine trying to create like lots of little line segments, distances from the mean here. A lot of these line segments would be really small. So a lot of their squares would be like very small or maybe non-existent in this case. And then, you know, the average red square would be pretty large. So are the values in B more clustered? No, they're not. And so statement one is not sufficient. Note, we're not solving for standard deviation. We don't have values. We're just trying to think about spacing and relative distance between sets or values in sets. Let's go take a look at statement 2. I'm going to do the same thing with my blue and red dots. Every value that's in list B is also in list A. Okay, like the easiest way to represent that is just like have a couple values in B and have the exact same values in A. Are the values in B more clustered than A? No, they're the exact same. So these should have the same standard deviation. So the answer to this question in this case would be no. I want to now see if I can satisfy statement 2, but get it so that like, yes, the blues are, or the reds are more clustered. The values in list B are more clustered. So maybe I could just like have the same starting set and then just like add some more values for A, right? Like every value that's in list B is also in list A, satisfied. But there's nothing that says every value in list A has to be in list B. So I can just add some distance to the outskirts of list A here, and that is going to make list A more widely spaced about its average than list B. So the answer here is yes, B is more clustered. And this is not sufficient. Oh, what fun. Now we get to combine these. So the nice thing about this last case that we just tried is that it also satisfies statement 1. So when I combine these two, I'm just going to go ahead and take like the equivalent of what I just did for statement 2 alone and bring it to statement 1 and say like, look, the answer here is yes, right? The range of A is wider and everything in B is in A. B is more clustered, so the answer is yes. And so now I want to try to get a no answer. Can I do it? Well, let me like go ahead and put these values here. Maybe I could just take what I just did in this first case, but now really try to compress the standard deviation of A. Let me get A more clustered than B. Maybe we're thinking ahead here. You just like shove a ton of list A values like right in the middle. So now we see, oh, list A is definitely more closely clustered than list B's values are. This is an answer no. And that means even when you combine them, we have not sufficient information. This is answer E. Yes, answer E. Whew, tricky. Yeah. I think like this kind of like these tricks of just like dumping like thousands of values in the middle or lots of values to the outside is kind of like how we want to think about this. We want to push things to the extreme. Like how large can I make one list standard deviation? How small can I make it, right? And just see like if there's room to kind of get different extremes, you know, if we can break the statements. It's how I like to do a lot of geometry problems, right? When it says like a rectangle has a diameter of 16, what's its perimeter? Like, well, I could make that like a pretty square rectangle, or I could make it like a really flat rectangle, and that would change its perimeter. So same kind of concept here. Answer E. All right, last one. Last one is fun. I tried to make the physics of this somewhat like correct, although I had to do some rounding. I also have no idea how much the average astronaut weighs. But this question is basically a combination of these topics. Remember where we said uniform change via addition or subtraction does not change standard deviation, and multiplication and division does. It changes standard deviation by the same factor. Question came in about that data sufficiency one. Would that be a hard question on the exam? Yeah, I'd imagine so. That seems pretty tough. I think this one's pretty hard too. So what is happening as we go from like Earth weight to moon weight of these astronauts? We basically have like a function transformation, right? The Earth weight we know is E for an astronaut. And when we put that astronaut on the moon in a spacesuit, this is what happens to their weight. Like you make it smaller and then you make it bigger. Right? So it's basically like a function question. Okay. So like, what does that really mean? Let's take a look at some of these transformations. Like suppose you have a ghost who weighs 0 units. Okay. And then on the moon, they also weigh 0 units, but then the ghost has to wear a spaceship. I don't know why the ghost would have to wear a spaceship. This wasn't a good example. They're already dead. But they have to wear they have to wear a spacesuit because that is the rule. And so on the moon, the ghost weighs 200 newtons. All right, let's imagine someone weighs 100 newtons. By the way, a newton is like a newton is like a fifth of a pound. It's like between a fifth and a fourth of a pound. So like 100 Newton person is very, very small. So like an infant. All right, so we've got this infant weighs 100 newtons on Earth. We put him in a spacesuit, put him on a spacesuit, and put him on the moon. And 100 times 0.16 is 16, plus 200 is 216. So we can see kind of these transformations. Their moon weights are actually going higher. I thought you were supposed to weigh less on the moon. Well, we continue this, and the transformations keep going. And eventually, like, yes, people do weigh less on the moon than on the Earth. It's just like the spacesuit weighs a lot. So we have to deal with that. So what does this look like on a number line? Well, if we plot the Earth weights on a number line, we can see they're uniformly spaced here from 0 to 400. And if we first just kind of do the first part of this moon weight function, we're going to multiply by 0.16. And so this has the effect of like mapping 0 to 0, mapping 100 to 16, 200 to 32, 300 to 48, and 400 to 64. Okay. So that's the first part. We've kind of compressed them. And then we have to add 200 here. So when we add 200, think about what's going to happen. All the values just shift to the left, to the right. Yes, to the right. It depends on stage right or stage left, but I'm looking at it. They shift to the positive end by 200 units here. So the effect is the spacing contracts. And just kind of thinking about how the spacing contracts might be enough for us to eliminate like answers C, D, and E, right? If the original standard deviation was 100 and now the spacing is a lot smaller, it can't be C, D, or E, right? The spacing has shrunk, so they're all close together. The values of the squares I would make of the distances would all be quite a bit smaller. And that should hold for kind of any data set we choose. I chose like a really convenient data set of just like every multiple of 100 from 0 to 400. But even if I like replace these with like some more typical weights of astronauts, right? You're just gonna have to trust me that I put in the values and I plug them into this equation. This is what it spit out. On Earth, we've got like this distribution of weights. And on the moon, what happens when we put them through this function is they all just kind of compress, right? And so we need like a much smaller standard deviation than 100. So now we have to ask ourselves, by how much did they compress, right? And the compression is the 0.16, right? Remember, multiplication is what, like when you multiply all the values by a certain factor, the standard deviation changes by that factor. And then when you add, the addition does nothing. So this is what that looks like, right? The first thing we do in our data set is we multiply everything by 0.16. So the original standard deviation should also be multiplied by 0.16. So we go from 100 to 16. The next thing we do to the data set is we add 200 to everything. That was that shift towards the positive end on the number line. Remember, those shifts without a stretch or a contraction, those shifts don't change standard deviation at all. And so the 16 stays at 16. So this one is answer A. Yeah. Yeah, the 200 doesn't play a role in the separation. It's like a, think about this as like as a function. Like if you graphed this line, like y equals 0.16x, right? The 0.16 is the slope, right? Which kind of measures how much y changes in relation to x. Every time x goes up 100, y goes up 16, okay? The 200, since it's consistently added, that's just the intercept, how far up that y equals 0.16e line goes, but it doesn't change the degree like how y, it doesn't alter how y changes with respect to x. Yeah. That's kind of a way to think about it. That was the end of the set. Yeah, believe it or not, that was the end. It seems kind of like an anticlimactic ending. But I did have a question in chat that came in, and it was like, what happens when you add a new value to your set? Like let's say you have a set and you add a new one. What happens to the standard deviation? And ultimately that depends on what that new value is. So one question that's come up before is what happens when you add a value to the set that's inside one standard deviation? And so I do have like kind of a visual to show here. This was our old set early on when we showed all the squares. But let's say we add a value right here. We'll call it Q. I don't know, this Q is underutilized. And it's clearly like within one standard deviation of the mean. What happens when you calculate the new standard deviation? And the thing I can tell you here, and I guess I could show you with an example, is when you add this new Q, what happens is you would add like a new square to all of your other squares. And because this square is smaller, it changes the average size of all the other squares, which means the average size of all the other squares has shrunk a little bit. So when you square root it, its side length has gotten smaller as well. And so if you add a new value within one standard deviation, the new standard deviation will be smaller than the original one. Unless you started with a standard deviation of 0, which is the smallest standard deviation you can have. That is when all the values are the same. So the other effect that this has is when you add Q, it does like change the average, right? It would change the average from 2 to something like a little closer to 2 now, because you've added a number above it. And so what it has like this cascading effect on all the little squares that we had. But the net effect is these squares that were over here would shrink by more than these squares get larger. And the proof here is like really hard. I'm not going to go through it. You don't need to know this, but what you need to know is that if you add a new value within one standard deviation of the set, the new standard deviation will always drop unless it started at 0. Yeah. And so like we could try that. I can prove it. We'll just go to a standard deviation calculator. I'm not saying like you should ever prove this, but I just want you to see it. Okay, let me just see. New share standard deviation calculator. All right, so I've gone ahead and plugged in some values into the standard deviation calculator. I've plugged them in to be very convenient. There's 9 negative ones, and there's a positive 9. So the sum is going to be 0. So when we calculate this, the sum is 0, the average is 0, and the standard deviation is 3. Okay. So actually, this shows you the standard deviation is 3. The standard deviation here is would like encompass all the values to the left of the mean, right? Actually, like all the negative ones are within one standard deviation of the mean. So sometimes standard deviations like can overreach like one side of the data set. So what this means is, what if I add a value that's one standard deviation away? Right? If I add a value that's one standard deviation away, I would add 3 to the set, right? Because the average is 3, so one standard deviation would be 3 or -3. So if I choose to just add 3 here, what we'll see is the new standard deviation is now less than 3. Yeah, the standard deviation dropped. And it doesn't matter, I could try this with -3. The standard deviation still drops. Yes. So you don't need to know like necessarily why that is. You just need to know that it happens. And to be honest, you might not need to know that at all. Yeah, but it came up a couple times. Someone asked it a couple weeks ago, and it came up in chat recently. You actually have a little bit of a window. Like you could technically add a little bit more than 3 to the set. I'll just show that too. Yes, so remember our standard deviation here was 3. I could actually like get away adding a little bit more than 3. So for example, if I add 3.1, which is like beyond one standard deviation of the original set, notice the standard deviation of the new set is still smaller than it used to be. So there is like a formula for that. As long as you add, this is like really getting obscure, but as long as you add your new value is less than the square root of 1 plus 1 over n, where n is the number of terms, times the standard deviation. As long as your new value is less than this far from the mean of the first set, you'll be able to shrink the standard deviation. Like, the proof for that is like beyond me. I just know it's true and I don't question it. All right, so I think that was a lot. I want to go through some of these bullet points I have. I have some takeaways for you. I know it's been a little bit or a bit over an hour, but I want to make sure that you have the takeaways too. So let me go ahead and bring this back and go to page, here we go. So whenever you see a standard deviation question, we want to think about that standard deviation represents relatively like how close or how far apart the numbers are clustered from their average. Generally speaking, you won't need to calculate it. And if you do need to calculate it, it'll be with like really, really like small sets. The lower the standard deviation, the more they're clustered towards their average, the higher standard deviation, the more widely dispersed they'll be. If you add or subtract a constant amount to each value in a set, standard deviation does not change. It's a big one. But if you multiply each value by the same factor, the standard deviation changes in the same way. Right? Yes, I'm using the flashcard templates that I've been pushing in previous prep hours here. If you add a new term within one standard deviation, the standard deviation will always decrease unless it started at 0. And when can the standard deviation be 0? Only when all the values in the list are the same. That's it. I think that's gonna do it. Yeah. So just remember that you've got some extra options for free prep. I hope to see you at another one of these events. I think I'm doing one in April, or see you in one of our trial classes. It would be great to see familiar names there. I'll stick around and see if there are any questions. I know I'm getting some in chat, and I will see if I can answer some. I'll go ahead and shut up the recording here. So if you watched the video on YouTube, thanks so much. Hope to see you at one of these events live.